Okay, YouTube, this is our first video in our module on systems of nonlinear equations and their solutions. And so I suppose what we'll be doing in this section is exploring systems of nonlinear equations. That is to say, up until now, we've been used to linear equations of the form ax to the first plus by to the first equals c. And in this video, what we're going to see is that we potentially might have some equation that looks instead like this, where we have, say, potentially like a squared x or a squared y or a squared both of them, or to the third power, something that's going to cause them to be nonlinear. So we're going to see that these systems actually contain different solution possibilities. We want to learn how to solve for them algebraically as well as graphically. So let's go ahead and start with this. We say a system of two nonlinear equations in two variables, also called a nonlinear system, contains at least one equation that cannot be expressed in this linear equation form right here. And so what we're going to see is a couple of examples right here that are nonlinear systems, and we can see that at least in both of these examples, one thing I want us to notice is that we're dealing with two variables. And so that's pretty important here. We have two variables and two equations. Regardless of the fact that they're nonlinear, we need two unknowns and two equations to solve for those two unknowns if they possibly exist. And so we can see in this first example, essentially what we want to see here is that this squared x causes this to be nonlinear. So that is to say, we can't express it as ax to the first plus by to the first equals c. And so we say that that x squared term causes this to be something else, and in this case a parabola. And we say over here we have y equals x squared, and so this would be another parabola, y equals x squared plus 3. We could say that x squared plus y squared equals 9. As a matter of fact, because we're squaring both x and y, and in this particular case because these coefficients are the same, without going too much into it, this is actually the equation of a circle right here. And so in terms of nonlinear, these are pretty standard nonlinear things. We say that now solutions to systems. Remember that with respect to solutions to systems, we're looking for any point x, y, as long as it's when we plug it back into both of the equations, we get a true statement. So we say a solution of a nonlinear system in two variables is an ordered pair of real numbers that satisfies both equations in the system. And so we say that the solution set is actually basically the set of all ordered pairs that do this. And so what we're acknowledging is the fact that essentially we could have more than one solution. And so the set of all of the points that works there, that's our set of solutions for the system. So we say, as with linear systems in two variables, the solution of a nonlinear system, if there is one, corresponds to the intersection points of the graphs of the equations of a system. And unlike linear systems, we say the graphs can be circles, parabolas, or anything else other than just two lines. So we're going to solve nonlinear systems using substitution method, as we've done in the past. And we would say that addition methods sometimes also work. So with respect to the graphical solutions, let's say that up until now we've seen things like y equals, maybe 2x minus 1 as a line, and y equals, negative x plus 2, and something like this, we say has a common point on both of their graphs, and therefore it has a solution to the system. But what if we were to do something like, perhaps make this an x squared, where all of a sudden now, when you look at this, we say, well, this system here, all the solutions of this linear equation, this red line, are on the line. We say all the solutions of the quadratic equation, this parabola right here on the blue line, do they have any in common? We can see that we open up the door for having maybe more than one potential solution. Or maybe, perhaps if I did this, I'll show you here, if I were to make this like plus 5, these two graphs would never intersect and therefore never have any common solution. So we're going to see some pretty crazy things happening. Circles and ellipses. I could load this up with all sorts of funky transformations going on. Something like this here, we say then the common solutions would be where these two graphs intersect. That's what we're going to be focusing on solving for, basically algebraically in large part, but supporting it graphically as well. So what we're going to do is we're going to take a look at basically the use of substitution method when it comes to solving a nonlinear system of equations, and then the steps that we take to do that, and also just kind of verifying it graphically and then having you try on your own. So we say the substitution method, involves converting a nonlinear system into one equation in one variable by an appropriate substitution. So that is to say that what we're trying to do is eliminate a variable by making a substitution in terms of the other variable. So we say the steps in the solution process are exactly the same as those we use to solve a linear system. However, when you obtain an equation in one variable, it says that this equation may not be linear. In our first example, the equation is quadratic. So what you're going to see essentially, and I've mapped out the steps here, is a series of steps that we're going to take in order to solve a system such as this right here. And so what I want you to notice is essentially this. We can already see over here on the right, we say that this is the graph of a parabola here, this thing that has an x squared in it. And then this thing down here where x to the first, y to the first, this is a line. But we can see the graph of this line here and the graph of the parabola. And so already kind of starting with the fact that this has two solutions, and these two solutions are going to be 4, 3, and 2, -3. Now what I want to do is basically how to emphasize how to support these algebraically. And so in this first example, what we're going to do is go through these steps here and see how we could come up with some similarities between what we've seen with linear equations, systems of linear equations before. So step number one is basically, let's solve this should say one of the equations for one variable in terms of the other. So essentially looking at both of these equations here, I noticed that, hey, you know, maybe it's really easy to get y by itself on this second equation. So what I'm going to do is I'm going to say, well, you know, if 3x minus y is equal to 9, what I'm going to do is I'm going to subtract 3x from both sides of this equation. I would get negative y on the left side, and we would get, I'm going to write this as negative 3x plus 9. And then what we're going to do is we can take everything times a negative 1, which would give us 3x minus 9. Now I'll put a box around this. This is our modified equation. I like to call this one the modified equation. We're going to come back and use this. Excuse me. But essentially what we're going to do is we're going to substitute this back into the first equation. And notice that we're going to be putting it in for this y value right here. And so what we're going to need to do is when we put this back into the first equation, we need to take out the y and put in a blank set of parentheses so that we can insert this entire expression. What we get is 2 times, and it's going to be plus 10 here. We're going to get 3x minus 9. And so let's go ahead and do this. Let's simplify both sides of this equation here. So step 2 we've already accomplished. It says substitute the expression from step 1, which was this guy, into the other equation, but it says solve the resulting equation containing one variable. So part of this is to, once we plug things in, really we need to simplify before we solve here. And so what we get on the right side here is after we distribute, I suppose, a 6x minus 18 plus 10. When we combine like terms on our negative 18 and a positive 10 here, we end up with, suppose, a negative 8. And if we were to subtract everything over to the left side now, what we want to do essentially is we want to set everything equal to 0, because since this is second degree, we're going to get something here that likely we need to solve by method of factoring. And so recall that with factoring, we want to get something that we can set equal to 0 and factor so that we can say if 2 factors multiply out to be 0, then one of those factors had to be 0. So essentially what we get here is a situation where if you know your factoring skills here, we would say 2 numbers that multiply out to be a positive 8 here that add up to be a negative 6 are these two. And so therefore we could say since x minus 4 times x minus 2 equals 0, then somebody here had to be equal to 0. And in this first case we get a positive 4 here and we get a positive 2. I'm going to put a box around both of these. And here's where this is different from linear systems. And I'm going to just be really clear on this. Typically with the linear system, we would have run off, we would have said, hey, you know, we've got some x values here, let's write our solution. But we're used to having only one, and clearly on the left here, or on the right side, we can see that we have 2 solutions, but what I want you to see is that we want to write them both separately, distinct. And so we're going to say that in our first solution, then we know 4 is our x value, and our second solution, 2 is our x value. And so with these two right here, essentially what we're going to do is just what we would do in a normal substitution situation, except for we're going to have to plug them in separately and record our solutions separately. So that is to say that now we know that x equals 4 in one potential case. Well, if y equals 3x minus 9, then really what we do is when we plug this in here, we get 3 times 4 minus 9. In other words, we get 12 minus 9, we get 3. So we get 3 here, and then when we go back and plug this in, let's see, y equals 3x minus 9, where we substitute in the 2 instead. 2 minus 9. We would get 6 minus 9, which is negative 3. And so we're going to fill this in, we say negative 3. And so one thing I want you to see here is certainly when you look at this graph, we can support this graphically, because looking at what we have here, we have 2 points of intersection at 2, negative 3, which was one of our solutions, and 4, 3 was our other solution. So how this is different from substitution in a linear sense is essentially that when you do your substitution, chances are you're going to end up with, say, a quadratic equation you're going to have to solve. Chances are, I'm just going to tell you right now, chances are quadratic. And so your method is going to be to set it equal to 0 and factor it. And if it doesn't factor, at least if it's in standard form, then we could use the quadratic equation to solve it. So here's what I want you to do. Essentially what I want you to try then is to solve this system on your own here. We've got x squared equals y minus 1 and 4x minus y equals negative 1. You can see this is very similar to the one we just did. And then come up with 2 different solutions here if they exist. And what I want you to do is then go over to desmos.com and type these 2 equations in differently or separately and see what the points of intersection are and if they support your solution algebraically. Cheers.